Hello, everybody, and welcome. We're going to turn our attention to network traffic analysis for our ITSY-2443 course, Computer Systems Forensics at Northeast Lakeview College. So objectives we want to accomplish during this, we want to talk about some of the common networking protocols that should be reviewed at this point for most of you. We're going to talk about installing and using Wireshark, which is a protocol analyzer. That's kind of our go-to tool, if you will, for traffic analysis. We're going to look at some samples and analyze some common and some uncommon application traffic. And then we're going to demonstrate how we can carve files out of a network traffic capture to recreate what users were doing. So the reason that we focus on network traffic analysis in our digital forensics and particularly incident response work, traditional forensics disk artifacts are becoming more and more difficult for investigators to retrieve. We have cloud services where we don't have physical control over the devices. There are lots of counter forensics or anti-forensics tools that bad actors implement to try and obscure their tracks. And so that network traffic analysis has become a critical component. Only memory analysis gives a better understanding of a system that was compromised. But for the most part, we say that network traffic really can't lie. You can encrypt it and we can obscure some of it, but it still is going to give us a really good understanding of what's going on inside of a network. We'll see things like scanning and enumeration attempts. We'll see system compromises. We'll see lateral movement, and we'll see data exfiltration, all by analyzing network traffic. So we talk about communication protocols, the basics, the foundational that we learn in our networking courses, right? Transmission Control Protocol, TCP, combined with Internet Protocol, IP, right, for the addressing. We have the Uniform Datagram Protocol, UDP. We have ICMP, Internet Control Message Protocol. So those are our pings and network messaging. But there's other protocols as well that we tend not to think about too much. So Bluetooth is a communications protocol. 802.11, so our Wi-Fi standards, wireless, VoIP, SCADA systems all use their own protocols. Wireshark actually can analyze a little more than 3,000 separate protocols at this time. And Wireshark is still, it's an open source product. So it's one of the reasons we lean pretty heavily on it in our network convention. So talking about naming. So if I were to say, okay, in the kingdom, Animalia, and the phylum is Chordata and Aves and Seriforms and Anatidae, and the subject is a semi-aquatic web-footed waterfowl with a flat bill. You're like, oh, that's a lot of stuff, and it doesn't really mean much. And so what we're talking about is a duck, right? Which, extra credit, right, also has the exact same weight as a medieval witch, if you get that reference. So as we're talking about these protocols, we kind of interchange application or protocol, application and protocol. I tend to use the term protocol, but many of you are going to recognize and say, hey, wait, that's an application. It's okay. It's just a confusing thing that we have in this particular field of study. So examples of that would be the file transfer protocol, FTP. It is a protocol. It uses ports 20 and 21, secure shell, port 22, Telnet, port 23, domain name searches, DNS, port 53 on UDP, 53 TCP is a zone transfer or an attempted zone transfer, HTTP, sort of web traffic, port 80, encrypted web traffic, the secure version, port 443, remote desktop protocol, 3389. So those are all, we say protocols in forensics, and they're sort of, yes, they're protocols, but we also refer to them a lot as an application. So try not to get confused as we work through. We mentioned that IP protocol, so Internet Protocol, our addressing. We have IPv4. IPv4 version 4 has 4 octets, right? 4 bytes for addressing, which gives a little more than 4 billion addresses. Some of the classes that we should recognize when we look at network traffic analysis, right? So if the first byte is 1 through 27, that should be a class A network. There are a little bit more than 16 million of those IP ranges available. If the first byte is 128 through 191, that's a class B address. So that gives us a space of 65,535 IPs on that network. If we see 192 to 223, that should tell us that it is a Class C network, and Class C networks probably the ones we're most familiar with, right? So smaller, gives us 254 usable IP addresses. If we see a .10, so the first byte is a .10, we should recognize that's an internal address using a Class A space. So again, you could have 16 million IPs. Most organizations are not going to need that many internal IPs, but they use it pretty considerably for subnetting out networks. And so if we see 172.16 and then .0 through 31, that's reserve space. That's a Class B internal. So Class B internals could hold, again, up to 65,535 addresses. 191.168.1, that's one we're probably most familiar with, right? That's reserved as an internal Class C network. It's probably what you have in your home. So you can put up to 254 devices on that. And then lastly, if we see that 127.0.0.1, that is a local host loopback. And so that means the traffic came from the local host itself. IPv6 is a little more challenging. We see IPv6 addresses using Wireshark. If we can still analyze the protocol, it's just not as easy for us to look at that and say, oh, that's an internal network, that's an external, that's a Class A, this is Class B. IPv6 is classless. It uses 128-bit addresses written in hexadecimal. So for math people, that's 34 times 10 to the 37th power number of addresses. That's a lot. I don't even know what that number is. When we see an IPv6 address written, we see it in 2 bytes and 4 bytes and a colon and 4 bytes and a colon. And so it's not an official name, but we tend to refer to that as 8 quartets, so 8 4-byte segments that make up our IPv6. TCP is by far the most common transfer protocol that we'll see. The packaging protocol, how is the data going to be moved across my network, right? If we think about mailing a package, we have the box that it goes in, and then we have an address label. So our address label, right, that's kind of the IP part, but TCP is the box we're putting our stuff in. All TCP sessions begin with a 3-way handshake. You should understand that term. If you don't, take a few minutes to look that one up. Important things that we're looking for: it has a source address, so where this is coming from. It has a destination IP address as part of it. We have a source port, we have destination ports, and then we have sequence numbers and acknowledgement numbers, because TCP tracks each and every packet, which is why I say we can reconstruct what happened, right? Because we can look at those numbering sequences and put things back in the right order. And then lastly, there's those TCP flags, which bad actors would abuse for network scanning and enumeration. So opening up Wireshark, this is the main console has 3 sections. So the top section is going to show the data traffic, right? So each packet is numbered as it's brought into Wireshark. We get a time stamp, and you'll notice that goes way down into the 100 millionths of a second, because network traffic is really fast. We have a source address, we have a destination address, we have the underlying protocol that's being used, there's a length, and then we have some information about what's inside of that packet. The center section gives us detailed breakdowns on what was included in that actual data packet. We can expand each of those, the frame or the Ethernet 2, and anytime we select a packet on the top, it will display in the center portion, so we can look at details, and then we can see the actual hex values that are being used in the bottom window. So this is an interesting one. We should be familiar with the TCP and ARP requests. So it's easy. You may not be familiar with that DNMP 3.0. And so DNMP 3.0, that's actually a SCADA protocol. So this is interacting with a remote system in order to make changes. But we see that it starts with the three-way handshake because it's a TCP connection. And so this is an example of SCADA protocols being pushed out across the network because they're using TCP/IP in order to do that. So we see the commands that are being given, unless it's encrypted, and a lot of our protocols are not encrypted. They weren't designed with security, right? We can see exactly what was submitted. So this one was, this DNMP 3.0, and it's read class 1. And so basically, that system is polling, right? Hey, who is, what systems can I interact with? What can I do? We see a follow-up response at packet, what is that, 35 to select, and then another one at port 39, which is operate. So if we were to think about that in a physical world, what happened, right? Someone across a network connection said, hey, let me see your interface. What are my options? Okay, I want to select this control and I want to operate it. So I want to select this valve and I want to open it or close it. I want to select this switch. I want to turn it on, turn it off. That's what's happening in SCADA. And this is why so an increasing concern for security researchers is if someone can access, gets access into your network and you have operational technologies like this inside of a network, it becomes quite an issue very, very fast for us. Another sample using Wireshark. So this is an example. If we look at our protocols, we see, okay, it starts with that TCP handshake, right? The SYN packet, the SYN-ACK, and the acknowledgement packet, right? Starts the same way, but then we see that they're using Telnet. So we could say this is kind of two, if you're saying what protocol is being used, technically the user's using the Telnet protocol, but the packets, the actual data is moving across the network using TCP/IP. We can follow, if we right click on a packet, we get a menu that says, hey, and drop down, and we can follow a TCP stream. And if we do that, we can see that entire Telnet login. We see that the login was test and the password sent was capture. We see the command was sent, which was the uname -a command. If you're not familiar with that, that's a way to tell a Linux system, hey, what architecture are you running? And then exit command was sent. If you're thrown off a little bit by that, the double lettering, right? So like test, TT, EE, SSTT, it's kind of a throwback from old school dumb terminals, because they would repeat when you hit a key on your keyboard, it would go to the server and it would repeat it back to the terminal itself. So you're seeing a little bit of a legacy sort of an implementation. When we see the actual network traffic, we're capturing every character as it's being sent and sent back to display on the screen. That's why we see that. The reason that the password, we don't see that as doubled up, because passwords aren't just in Linux, right? Passwords are not displayed back to the screen. And so we only see that as one. So good thing to remember, unless my traffic is encrypted, any commands that are sent, anything that's done across the network, if someone has a capture device set up, if they're recording the network traffic, we can go back and replay and see exactly what a user did. So again, application was Telnet. The network protocol is TCP. Was it encrypted? No, because we could see the password, right? The login was test. The password was capture. The command used was that uname -a. And then we see that the remote system was running that Linux ARM architecture. So a secondary sample that we have, and this is going to be much longer because it is, right? So we would say the protocol that's being used, we see it highlighted there, is HTTP, right? Hypertext Transfer Protocol. This is web traffic. Web traffic, most networks, it will be the bulk of what you see. One thing to point out, Wireshark color codes the protocols for us, color codes the packet, so we can kind of see on the far right, It's a little difficult to tell on my screen, but you'll see it when you use Wireshark. You see a band on the very right, and it'll show you all the different color breakdowns. So you can kind of skip to different parts. It shows you an overview of what the network traffic might look like. This system or this session begins. Again, three-way handshake, because it's going to run the data across TCP. And then we say the protocol is HTTP. The command specifically is being sent that we see on the information, right? It's a GET command, which is the way a web browser typically goes to a web server and says, hey, get this and bring it back to me. But if I look in my bottom where I see the actual data that's being sent, I see the GET command, but I also see that the client is using a wget command. They're not using a browser to do that. And so this is someone using a command line to access a web server and try and download a file. In this case, it's that file logo.png. So if I were to right click it and say, hey, follow this UDP stream, I can see that a little bit easier. I see my Linux GNU, I see my wget command, I see my server's response. So I see that the server's running Nginx version 0.8.53. By the way, this is all network traffic works this way. There's no way to prevent a bad actor from seeing your server software. This is just built into the protocols. We see things like modified times or last modified time for the file that's going to be downloaded. Some other interesting, it says that it's not encoded, it's not encrypted. We do see that it's a .ping command, but then we see nothing but kind of garbage for us because this is a graphic file. And so it's not like Telnet where I'm seeing commands that go beyond that. This is a user trying to download a file. I could save this information, carve it out, go into a hex editor and try and reconstruct it if I wanted. But there's an easier way to do this in Wireshark. If I click on File, and there's an option saying Export Objects, and I say I want to export the HTTP objects, then I get a pop-up box that says, here is the object that was downloaded, right, using HTTP. It's that logo.png. I can download it or save it off to a different device, or I can click preview, and we would see that it's actually this logo, right? This packetlife.net logo. It's not very impressive. It's a very small network traffic capture file that we're seeing. Most capture files are much, much larger. You may have multiple files that are being downloaded from web servers, and so you'll have a really long list to look through. But the important point being, any file that's being moved across, if it's not encrypted, we have the ability to see it. We can see the actual file, we can see the images, we can see commands that were sent across. This is why we like these network traffic captures. So the protocol running was HTTP. The traffic was initiated with a wget command. The server, I mentioned that, right, is running Nginx. It's not encrypted. The file downloaded was logo.png, and then the file actually was a logo image that we saw in that particular example. So here's one, same things, right? Non-encrypted traffic, but now the protocol being used is FTP. So I can see from packet one, right, this FTP connection, and I see that the response, I see the server is running as this FileZilla server, 0.9.53 beta. I see a username put in as user1 and a password, which was Cyber Skyline, and it was incorrect. And so I see a second, right? User1 trying to log in using the password Metropolis, and then they're actually logged in. So I can track that behavior again using this network traffic. Again, FTP is not encrypted. So I see the commands that are going across. FTP being port 20. So keep that in mind. This is important. If I right click and follow the stream, right, then I can see, and here's the trick of it. So if I follow the command stream, I'll just see commands that are being issued back and forth. If I follow the FTP data stream, right, port 20 and port 21, we have two different ports, two different TCP ports being used. One is used to send commands, the other moves the actual files. So if I follow the FTP data command, then I can see what happened when the user issued that list command. And those are the files that were reported back from that FTP server, right? Bank.cap, FTP-cap, launchcodes.jpg, lincolnbedroom.cap, and securitycodes.txt. Those are the files that were sent across, and I can track what my user is doing. If I follow that stream for the raw data of a file, now it's a little complex. So if I follow the stream, I have a way to display it. So typically it displays in that ASCII 2, and we see in the center a drop down. And if I change that to raw, it will show me the raw hex values. I can save that file, and I've saved the actual file that was sent across, whatever it is. If it's a zip file, if it's an image file, if whatever was being sent across this FTP stream, I have the ability to capture that. So hopefully that gives you a good, at least a minimal understanding of what Wireshark is all about. Now we're ready to get to work on your network traffic capture project.